We're going to take a look at increasing and decreasing functions. This is something that we've already studied in college algebra. So remember the definition. Increasing function is a function as you travel along the graph moving in the direction from left to right, and it increases. You're going up as you move, then it's an increasing function. And as you go from left to right and it decreases, it goes down, it's a decreasing function. So now I'm switching to increasing and then decreasing again. So it's pretty easy to figure out what the intervals are if you see a graph. Well, we're going to come up with a way to figure out how to tell the intervals when it increases and decreases just from the equation. And we are going to have then see if the derivative can help us. So if we want to use the derivative to help us determine if it's increasing or decreasing, remember what the derivative tells us. So when we do the derivative, we're looking at the rate of change, or we're looking at the slope of a tangent to the curve. So when the curve is increasing, what is the slope? Well, the slope is a positive number when it's increasing. And when it's decreasing, our slope is always a negative number. All right, well, let's take a look at two functions that we're very familiar with. Excuse me. And let's test this and see what happens. So if we have y is equal to x squared, all right, we have three things we want to do here. First of all, we want to sketch the graph. So I'm going to make a little sketch right here of y is equal to x squared. So it's going to look something like this. Determine the intervals of increasing and decreasing. Well, as I start from negative infinity and I travel along the curve all the way till I get to an x value of 0, on that open interval, I see that it is increasing, or I'm sorry, that it's decreasing. And then from 0 to infinity, it is increasing. All right, so now we're going to compare that to the derivative. So if my function y is equal to x squared, the derivative is 2x. And if I pick any number that's to the left of 0 here, and I plug it into the derivative, so I'm going to take a negative value for x, and when I plug it in, I get a negative number. So over here, on this side of the graph, it's always a negative number. The slope is negative, so that means the curve is decreasing. And if I pick any number in the interval from 0 to infinity for x, and I plug it into my derivative function, I get a positive number. So if my slope is positive, that means that it is increasing. All right, let's take a look at y is equal to x cubed. Okay, so a quick sketch of that graph. Would look like that. Determine the intervals, it's increasing or decreasing. Well, it's increasing over the whole function, so from negative infinity to positive infinity. So let's compare it to the derivative. So my derivative, I'll write it on top here, is 3x squared. And if I take any number, any negative number for x, and I plug it into the function and I square it, I'm going to get a positive. And if I take any positive value for x, and I plug it into a squared function, my derivative, I'm also going to get a positive. So I have slopes that are positive all the way across that curve. So that curve is always increasing. So at what x values would the graph change from increasing to decreasing or vice versa? Well, let's take a look once again at the y is equal to x squared. And I see that over here then, from negative infinity to 0, it's a decreasing function. And from 0 to infinity, it has positive slope, so it's an increasing function. So it switches over right here. All right. On my cubic function, y is equal to x to the third, it was positive here and positive here. So at this point, it did not change on either one. But what's happening here is on this particular curve, it changed from decreasing to increasing at this point here, which is referred to as its minimum. So we could have this occurring at minimums. We could also have it occurring where the slope is undefined or 0. So like right at this point here, remember our slope is 0. So, but then I check on either side of it and it's still increasing. So we can look at values then where the derivative is undefined or where the derivative is 0. And these values then are referred to as critical values. Now the other one that I don't have shown here would be a maximum. So if I have a curve that looks like this, so it's increasing, and then at this point it switches to decreasing, and at this point it switches to increasing again. So we could also have changes in direction from increasing to decreasing or vice versa at maximums. So the definition of a critical number is if a function is defined at c, then c is a critical number if the derivative of the function at that value c is 0, or whenever the derivative of a function is undefined. So either one of those two things. So we're finding the derivative first of all. Whoops. So we're finding the derivative first of all, and then we're setting that derivative equal to 0. And we're finding all the points that make it equal to 0. And then we're also looking to see where the derivative is undefined. Those are our critical points. Okay, so here are the guidelines then. So given a function, the first thing you're going to do is find the derivative of it. Then you're going to locate the critical values. So you're going to look at zeros or where it's undefined. And then you're going to set up these different intervals from your critical values. So if I only have one critical value, then I'm only going to have 2 intervals to test. If I have 2 critical values, I'm going to have 3 intervals and so on. And then you use the test. So we just look to see, well, is the derivative positive or negative in those intervals? All right, well, let's try it with a function that is has a little bit more going on than the x squared and the x cubed. So let's take a look at this one. Find the open intervals on which the function is increasing or decreasing. Okay, if you go back to those guidelines and look, the first thing we have to do is find the derivative. So we would get 3x squared minus 3x. Okay, then we find the critical values. So we set the derivative equal to 0. And we solve it. We look to see what are all the points that make it equal to 0. So I can factor out a 3x. So I get an x of 0 and I get an x of 1. We also have to look at where the function is undefined. and it's a quadratic function, so it's never undefined. So these are my only two critical values. So from those critical values then, we set up the intervals. And it's always just open intervals. So I have to go in between those. So we need to go from negative infinity to 0. And then we have to go between 0 and 1. And then we have to look at all values greater than 1. So from 1 to infinity. So at two critical values, we have 3 test intervals. All right, now we're going to take a test value in each one of those. So from negative infinity to 0, I'm going to take negative 2. From 0 to 1, I think I'll do a half. And from 1 to infinity, let's do 2. So now we plug that value into the derivative. It's very important that you plug it into the derivative, not the original function. So we go into here, and if I plug in a negative 2, I'd get negative 2 squared is 4, times 3 is 12, and then negative 3 times negative 2 is positive 6. So I'm adding them together, they're two positives. So it's a positive interval. And that means if it's positive anywhere in that interval, then it increases. It's increasing then on the interval from negative infinity to 0. Okay, let's plug in the 1/2 into the derivative. 1/2 squared is 1/4. 3 times 1/4 is 3/4. And then minus 3 times a half, so minus 3/2. Well, that's a negative 3/4, but we're just interested in the sign, so we'll go with negative. So therefore it's decreasing on the interval from 0 to 1. And then the 2, we plug in a 2, and we get 2 squared times 3 is 12. 12 minus 6 is 6, so it's positive. So it's increasing on that interval also. Okay, let's try one more. These are kind of ugly functions, aren't they? So you probably can't. I kind of like these because you can't automatically, in your mind picture what they look like. So we just have to use our calculus. And we have to use our test here. So the first thing we do is find the derivative. Okay, in order to do this derivative, we have an outside function and an inside, so we have to do the chain rule. So 2/3 times the function to 1 less power times the derivative of the inside. Okay, so there is our derivative. Let's simplify it a little bit, make it into a fraction. So 2 times 2x is going to give us a 4x. And in the denominator, we're going to have a 3. We're going to have the cube root of x squared minus 4. I'm going to change that x squared minus 4 to x plus 2, x minus 2. Because what we use this derivative for is to find the critical points. So the critical points occur at zeros. So our zeros, well, the only thing that's going to make the fraction equal to 0 is when the numerator is equal to 0. So that's just going to be at 0. So I have a 0 at 0. And then also where it is undefined. So undefined, because I have a fraction, I look in the denominator. I can't have a 0 down there. So it looks like it's going to be undefined at -2. And then also at 2. So I have 3 critical points. I'm going to put them in order then. So from smallest to largest. And if those are my critical points, then our intervals are going to be from negative infinity up to -2. And then from -2 to 0. and from 0 to 2, and then from 2 to infinity. So 3 critical points gives me 4 intervals to try. So then we find a test point in each one of those intervals. Let's do -3 here, -1, 1, and 3. So we plug these into the derivative. So we're going to plug those values into here. Alright, so when I plug in a -3, keep in mind, we don't care what the number is, we're just looking to see if it's positive or negative. Okay, so when I plug in a -3 in the numerator, I'm getting a negative number. In the denominator, a -3 plus 2 is a negative. A -3 minus 2 is a negative. So a negative times a negative is a positive, and the cube root of a positive is a positive. So it looks like I'm getting a negative number there. And if it's negative in that interval, then that means it decreases. So the function is decreasing from -infinity to -2. All right, now let's take -1. Plug it into the derivative. 4 times -1, well, that gives me a negative in the numerator. And the denominator, -1 plus 2, that's a positive. -1 minus 2, that's a negative. Positive times a negative is a negative. And the cube root of a negative is a negative. So that's going to be positive. So that means it increases on that interval. Plug in a positive 1. 4 times 1, well, that's a positive. 1 plus 2, that's a positive. 1 minus 2, that's a negative. So we multiply a negative, cube root is a negative. So should be negative on that one. And then the last one, 3. Well, the numerator will give me a positive 12. The denominator, 3 plus 2, that's positive. 3 minus 2, that's positive. Positive times positive is positive. The cube root being positive. So it's increasing on that interval because the derivative is always positive. Okay, so that's what it looks like. So you're going to now find the find where functions are increasing or decreasing using the derivative instead of just looking at the graph of it. And then it's always nice to take a look at the graph, and verify what you've done. All right, so that's all we have for this one. So good job. See you in class.